Hello everyone, can you hear me? If you can hear me, please type yes in the chat box. Okay. So, hello everyone, and welcome back to a new webinar hosted by SPE Beirut section. My name is Qasim Al Aqla. I am the Young Professionals Chairperson at the SPE Beirut section, and I'm going to be the moderator of the webinar today. Our webinar for today is very special. First of all, it's on a reservoir engineering topic as you have requested before. And second, it's going to be presented by our first female speaker, Miss Vanessa Glass-Neal, who is joining us right now from the United States. Miss Vanessa,
Hello.
yeah. So Miss Vanessa is a reservoir engineering consultant at Sadlands Energy. In her previous role, she evaluated international and domestic waterflood assets at Apache Corporation. Neil has more than 14 years of hands-on experience in the oil and gas industry with a focus on conventional play redevelopment and additional skills in managing unconventional assets, production operation, simulating reservoirs, acquisition evaluations, and monitoring young professionals. She holds a BS in petroleum engineering from Texas A&M University and an MBA from the University of Houston. So I'm pretty sure you are going to enjoy and benefit from this webinar today, especially like with an expert like Mr. Vanessa. Please, if you have any question, type it to the chat box so Ms. Vanessa can answer all of them at the end of the webinar today. Without any further ado, Ms. Vanessa, over to you.
All right. There it goes. All right. Hello. Good evening to everyone today, or good morning, or good day, depending on where you are in the world. My name is Vanessa Neal, and so just to set some expectations for the talk today, what I'm going to be going over are the basic concepts really that I found useful in my career of evaluating water floods. And I'm not going to dig into a lot of equations today. I'm really going to focus on the concepts and how they can be used. Because I really feel that building that foundation, that understanding, is what will help you the most. So just very briefly, since it's already been kind of covered, I have right at 14, 15 years experience in the industry working for both operators and service companies. I've evaluated and optimized water floods all around the globe. I'm experienced as a modeler and a simulator, and I just recently founded Sethlins Energy as a consulting group. So what I'm going to be going over today, again, a little bit more detail this time. It's an introduction to water flooding, like what is water flooding. Then I'll be going over patterns, geology, reservoir fluids, reservoir and fluid properties, and how they all affect your water flood's efficiency. And then hopefully we'll still have time and I can go into some surveillance plots and build on how you use that foundational concept knowledge to interpret surveillance plots and use them to understand and optimize water floods. So what is water flooding? It's generally referred to as enhanced oil recovery or improved oil recovery. And it's defined as a method of secondary recovery, which means that you inject water into injectors and you push oil to producers. Mechanically, that's what a water flood is. But to really understand water flooding, I think you need to ask a different question. Instead of what is water flooding, why do we water flood? Right? Because it's not just to get oil out of the ground. You can get oil out of the ground during primary recovery. There's some kind of drive mechanism that exists in the reservoir already, usually a pressure drive, and that's what pushes oil out of the ground. So why do we water flood? Water flood is a secondary recovery method, and what you're doing is you're introducing energy into a depleted reservoir or into a reservoir system in order to re-energize it and to move oil that would no longer move because your hydrostatic head was equal or above your reservoir pressure, and you're raising that reservoir pressure so that now the oil can move out to your producers and out of the ground. So it's not really about pushing oil to producers, although that is a good function of water flooding. It's more about re-energizing the entire reservoir system so that oil becomes mobile again. And usually the effectiveness of your water flood is measured on recovery factor. You do this for fields, whether they're water flood or not. So a lot of fields, and there are exceptions of course, but a lot of fields have a primary recovery factor of anywhere from 5 to 20%. And when you introduce a water flood, you're looking at an incremental recovery, usually ranging 15 to 25% on top of whatever that primary recovery was. But when you compare recovery factors, you need to be aware of where that number is coming from, because not all recovery factors are equal, and you want to make sure you're comparing apples to apples instead of apples to oranges, right? So the most influencing number that could disrupt a comparison of recovery factors is your original oil in place. A lot of people will use gross original oil in place. So that's just counting all the oil that exists in the reservoir, and that's great. But what that can do is, especially in a water flood, that can result in a lower recovery factor than what you might expect because you're including all of the oil, right? And then there are some people that are like, well, this is a water flood, so my original oil in place is only going to be the oil that is floodable. And so that will create a much higher recovery factor because it's a smaller volume of oil than what using a gross oil in place will do. And this is just kind of an example right here, net pay versus floodable pay. So net pay, which would go to a gross oil in place, is just any pay that has oil in the reservoir, right? But if you're looking at floodable pay, then you're looking at the reservoir that has the properties in which water will flow through it. You're looking at the pay that is connected. And sometimes we know which pay is connected and which pay is not, so it can be tricky to identify a floodable pay. Again, this is really just to make sure that when you are comparing recovery factors between floods, you understand where that number is coming from. All right. So as I said, I've shown you two formulas and I said I wasn't going to get into them, but there's only like one more after this, so don't worry. So, and this is not a traditional formula. This formula for sweep efficiency is what I would consider more of a conceptual formula. And the reason for that is the three efficiency numbers, your aerial sweep efficiency, vertical sweep efficiency, and displacement sweep efficiency. Those are not measurable numbers. These are basically guesstimates. But what's good about this formula is it kind of defines the three components that go into determining if your water flood is efficient or not. So the one that is probably, of these three, we can attempt to control probably 2 out of the 3. And that would be the aerial sweep efficiency and the vertical sweep efficiency. Those we can actually interact with our wells, with our reservoir, and attempt to control those. Displacement sweep efficiency has to deal with the rock properties and the fluid properties, and we have very limited control on this. And I'm in the next few sections, I'm going to go over each of these different variables and just kind of explain the concepts behind them so that you can understand what we control and what we can do to improve water flood efficiency. So we'll start with aerial efficiency, and we're going to start with this one because it's first in the formula and it's also the one that we probably have the most control over. And how we control it is with water flood patterns. So this is a sampling of kind of the standard water flood patterns. And if you think back to why we water flood, purpose for a water flood is to re-energize the system. To do that, more times than not, you want to have a larger number of injectors because you're trying to replace all of the production that's already existed. And you're trying to fill that voidage and get the reservoir pressure back up. So that's why when you see the patterns that have a higher injector to producer ratio, they're often called normal patterns because most of the time this is your ideal form. Now, a lot of operators don't view injectors as wells that make money. They say, well, producers make money. Those are the ones that produce the oil. So that's what I want to drill. I want to drill producers. I don't want to drill injectors. So that's why across the industry, what you're normally going to see are inverse patterns in which you have that higher producer to injector ratio. Now, if you have a pattern that doesn't fall into one of these, more than likely it's going to be an irregular pattern or something that we call a peripheral pattern. A peripheral pattern is where you drill injectors along the oil-water contact or at the low end of a structure. And the thought behind this is that these injectors will support the wells that are higher on structure by injecting at the bottom, and then the water will just flow up to your lower pressure sinks. And ideally that could be the case, but in most of my experience, as long as if there's not a strong aquifer presence, which is the only time I really see the theorized flood front actually happen, if there's no aquifer presence, then what you're more likely going to see is the water following the path of least resistance. And what it's going to do is go into the aquifer, because the aquifer is probably going to be the same pressure or less than what's going on up dip. But they also, water likes to flow against water. You know, the relative permeability, the less resistant flow is into the aquifer. And so that's where water is going to go. So if you're trying to improve aerial efficiency, you normally want to stick with a standardized pattern, which is those geometrical shapes that we've seen before. And I'm going to go over a few of these just to give you an idea of like where they can be useful and how they're useful and how they're not really. So this is a normal 9 spot pattern. And I said before it has a higher injector to producer ratio, but when you're looking at the pattern itself, it's not 8 injectors and 1 producer. Instead, when you're looking at that geometric area that's been outlined, you'll see you're only getting half of the injection for several of these wells inside this square, inside this box. And for the corner wells, you're only getting a quarter. So when you add up the halves and the quarter, you're really getting a 3 injector to 1 producer ratio. And same thing if it's the inverse, you're really only seeing 3 full producers to 1 injector. The unique thing about a 9 spot pattern is that if you're ever to downspace, you have the option to downspace in 2 different ways. The first of which is you can downspace into a 5 spot pattern, which is much more efficient than an inverse 9 spot because it's a 1-to-1 ratio on producers to injectors. So it's much easier for an injector to keep up with 1 well than it is to keep up with 3 wells. The other way that you can downspace a 9 spot is to a direct line drive. And again, this has the same efficiency as a 5 spot pattern. It's got that 1-to-1 ratio. But although all the injectors, all the producers are lined up, this pattern is more useful than a 5 spot when you have a very strong directional flow in your reservoir. That way you're able to orient and kind of guide where your flow will go. The next patterns that I've seen in several fields are 7 spot patterns, and they are often referred to as chicken wire patterns, which is why I have that picture. First time I heard it, I was like, why is it called chicken wire? It doesn't make sense. But if you see the picture, you're like, okay, that makes sense. So in the chicken wire pattern, you end up having, in the normal one, you have 2 injectors and then 1 producer. Inverse, 2 producers, 1 injector. And this pattern actually downspaces to a 4 spot pattern, which, like the 5 spot and the direct line drive, has your 1-to-1 ratio. The fields in which I've seen a 7 spot pattern used are fields in which the rock properties in the reservoir or the fluid properties mean that the oil are not going to flow very well, and so you're going to need tighter spacing and mainly tighter spacing. So why do I say that water flood patterns improve aerial efficiency? Well, that really comes down to flow dynamics, right? So as I said before, fluids in the reservoir, they're going to flow the path of least resistance. That's just kind of a rule of nature. And if all of your wells are in an oil-bearing reservoir, and you're not having to worry so much about the relative permeability factor, like you would if something that's close to an aquifer, then the next overbearing parameter, I guess, is going to determine where something flows is going to be your pressure. And the flow will be from high pressure to low pressure. So, you know, producers pull on the reservoir, so they're your low pressure sinks, and injectors push in water into the reservoir, so they're your high pressure. So generally flow will be from your injector to your producers. I've shown, so the streamline image right here is showing potential flow paths between an injector to a producer, and I have them colored by pair. So these are all the potential flow paths that that water an injector takes could flow to a producer for each of the 4 producers in this inverse 5-spot pattern. So the thing that's kind of unique is that you'll see you don't have flow crossing between producers. And this has to do with the forces that each of these producers enact on the reservoir. As I said before, they're pulling. So they're pulling oil towards them. And then at some point in between those 2 wells, the force at which they're pulling is exactly the same. And so at that point, the molecule oil that is receiving a identical force from each of these producers is just not going to flow anywhere. And that's what creates those no flow boundaries between producers. When you have more than one injector, they create a similar boundary. So instead of pulling, they're pushing injection water in, they're pushing, and then at some point in between the 2 injectors, you're going to hit a point where they're pushing an equal amount of force. And that's going to create what I call a pressure boundary. And in an inverse water flood pattern, what you're really seeing, the red lines drawn for that pattern, those are generally supposed to be your pressure boundaries that your injectors create. So the reason that geometric patterns improve your aerial sweep efficiency is that you are able to control flow with them. The more injectors that you have, the more your patterns are spread across a field, the more you're able to control the flow. So if you have an injector that is surrounded by other producers and injectors, then the flow, the area that injector is sweeping is controlled to just basically the geometric pattern that's been drawn for it. And what that allows you to do, it reduces your response time that you'll see in your water flood. You have a measurable volume that's identified by your pattern area. And it just allows you, allows a much more efficient flood because you know where your water's going and you know what volume of oil you have to sweep. All right, so I've shown you a bunch of different patterns. What's the best pattern? Well, when you think about what's the best, you have to go back to what is your goal, right? So the goal of water flooding is re-energizing the system and sweeping your oil from your injectors to your producers. So the best pattern will allow you to inject as much energy as you need and to sweep the oil efficiently. There's no one right answer. It really depends on what's going on in your reservoir and what's going on in your field. You have to take into account your surface equipment capacity, what kind of water supply you have, if you have any regulatory limitations, and then also what's economic. So I may be able to drill, 50 injectors for 10 producers, and that's going to inject a lot of water, and you're going to be able to re-energize the system. But is it economic to do that? And, and that just varies depending on the field. All right. Now we're going to go into vertical efficiency, and I'd say probably the dominating force in vertical efficiency has to do with geology. So a lot of times when we're injecting or thinking of a reservoir, we think of it as a single zone. That's not really true. Most of the time we're dealing with a bunch of layered beds on top of each other that create that single zone. So you're often dealing with a stratified reservoir. And when it comes to a stratified reservoir, whenever you're injecting water, each of those different beds or zones will have their own properties, and the water will flow through them differently. So in this example, in this picture, you can see that one of the zones has already, you've already got a direct line of injection between the injector and producer, and you've started to see water break through. That doesn't mean it's time to shut in that producer because we've gotten water and we've swept all the oil. It just means, hey, we've got one zone that has really good permeability, really good porosity, something that's potentially a fast zone, and we got early water breakthrough. And that's okay. It just means that we're gonna have to cycle the water and continue to sweep the rest of the zones, and also to continue to sweep that zone, because what you get water breakthrough first on is your most direct path. If you think back to the streamlines, there's still a lot more area to sweep even in your fast zone. Now, if you get to a point where so much water is breaking through that you're starting to have issues dealing with it, then there are common workovers that you can implement in order to reduce the water or reduce the fast zone, isolate it, break it off, something. Two different options that I'm aware of. I know there are more, but these are the most common that I've seen used. There's a cement squeeze, which is going to be, you could actually do it on either the injector or the producer, but it's going to be near wellbore. So you need to know, I guess, if that fast zone is isolated, if it has impermeable beds above it and below it, so that it can't communicate vertically with the other zones. If that's true, then it would be a good candidate for a cement squeeze. If the fast zone can communicate with the other zones vertically, then it's going to be a very limited limited solution. So you plug it off, say at the injector, the water starts to go into the other zones, but as soon as they can, they'll go back to that fast zone, because again, that's the easiest path for the water to flow in. Polymers will go deeper into the well. And that sort of thing, you would pump polymers into your injector, and they're usually timed in some chemical reaction, and they'll go the fastest paths for your flow, and then they'll set up and make those paths impermeable. The problem with that is that you've just plugged off your best avenues of flow, right? So all you're going to have left after that are your less desirable paths, which could be good because you could be sweeping better oil, but it's just something to be aware of. All right. Another way to address vertical efficiency is making sure that your wells are in conformance. So I've outlined the perforated intervals for the injector and the producer in red in this picture. And you can see the producer is only producing from 2 zones, but you have injection in all of the zones. So if the other zones are taking water, then you've lost a lot of efficiency in your injection. You basically created a, 50 or 60% leak off for this injector just because the producer is not producing from the same zones. And one of the last things I'm going to cover for vertical displacement or vertical efficiency is gravity segregation. So ideally, the injection will sweep uniformly across the zone. You know, from top to bottom, you just have a block and it's sweeping. Unfortunately, as I've already pointed out for several other reasons, that's not likely to happen. But whenever this zone or bed gets thicker, what you'll tend to see is something called slumping or sagging of your flood front. So, and gravity is basically pulling the water down. Oil is lighter than water, so it's going to migrate up to kind of the top of your zone, and you'll only really be flushing or flooding the bottom part of your zone. One way in which you can get around this to create something that's closer to a uniform front is through wagging. So alternating water and gas injection. So gas is going to be lighter than oil, and so it's going to tend to propagate at the top of your zone. And so by alternating your water and your gas injection, what you end up doing is creating a semi-uniform flood front across your zones. All right. So the last thing that we're going to going back to that equation, is going to be the displacement efficiency. And this really has to do with how is your oil moving through the reservoir. So one thing that affects this is going to be the mobility ratio. So mobility has to do with how easily the oil moves in reference to something else. In a water flood, how does the oil move in reference to water? All right. So that's mainly determined by your relative permeability and your viscosity. So if your mobility ratio is less than or equal to 1, then you're going to get piston-like displacement. And a mobility of less than or equal to 1 means that your oil is moving faster than or the same pace as your water. That way, when your water says, hey, move, oil says, okay, I'm moving with you. If your mobility ratio is greater than 1, that means your oil is moving slower than your water. So it's kind of like that angry driver behind you on the freeway, and he's like, hey, move, move, move. And you're like, I can't, there's traffic. And then they kind of sweep in between you, right? So that's what the water's doing with the oil. They're fingering through, they're sneaking tendrils through the oil because the oil's moving so slow. They're just trying to get by. They want to go. When you have a mobility ratio that's greater than 1 like this, then what you end up doing is having a lot of water cycling. So you can have water cycling in a water flood for multiple different reasons. You could have fast zone, as we talked before. You could have just a poor mobility ratio. You know, there are lots of reasons. So the other thing that we need to be aware of is what can affect our mobility ratio. As I said, it's dependent upon your relative permeability and your viscosity, right? So the things that can change your viscosity of oil, if it's a live oil, is pressure. We always recommend that if you can, you want to start a water flood before you reach bubble point. And the reason for this is that if you have a live oil, then you have gas dissolved into your oil. As the pressure drops and you approach bubble point, that gas starts to expand and your oil actually becomes more mobile because it becomes a little bit lighter with the gas being bigger in it. But once you fall below the bubble point, then the gas comes out of solution of the oil and you start having free gas in the reservoir, which is very mobile. But your oil that used to contain the gas has become less mobile. Its oil viscosity is increasing. And it's just going to become harder to move it. So ideally, water flood before you reach bubble point. That's usually not the case. It's usually after is when they start water flooding, is after you've reached bubble point. And all that really means is that you can still water flood. It's just that you're going to have a less efficient water flood because you've lost oil mobility. And there are additional influences. There are probably more than this. So these are just the ones that I thought of when I was, making the slides. But you have reservoir properties that will influence your mobility, porosity, permeability, your saturations, what's your wettability, capillary pressures, things like that. And then fluid properties, like we've discussed, your viscosity, if you have gas in the oil, and then your relative permeability. All right. And now you've got a really good foundation, I think, of what are the basic concepts and understanding what's going on in the reservoir that can affect your water flood and its efficiency. And now we're going to take those and kind of apply them to some surveillance plots to improve our interpretation of those surveillance plots. And then think about what does that mean for the water flood, and how can I use that knowledge to optimize the water flow. So first off, before I get into the plots, there are lots of different evaluation methods that you can use. There are rule of thumbs, analogs, equations, surveillance plots, models, simulators. There's no one best way to evaluate any kind of problem. And the best method really is to use a combination of these or all of them to get a true picture. But what we're going to go in today is the surveillance plots. So with surveillance plots, you really need to use them not just on the well level, not just on the pattern level, and not just on the field level. You need to look at them at all of the different levels because each one will show you a different picture. I'm just going to go over field plots this time, but I've kind of color coordinated it so you can see where you could apply the same plots at different levels. And these are not the only plots you can look at. There are lots of other plots that are really useful, but for time's sake, these are the ones that I'm going over. So a production plot can tell you about the timeline, and you will need to do, of course, research into the field and know a little bit about the wells and everything as well. But they can tell you a lot just looking at production plots that are rate time. There's also the oil rate versus cum oil, which can give you a very rough estimate of your reserves at different points in time in your well history. And it's a good kind of gut check against your decline curve analysis as well. Your voidage replacement ratio tells you how you are doing in managing your reservoir pressure and filling the voidage of everything that you've produced previously. Your recovery factor versus an injected pore volume is good just time to visualize and use with analogs really to see if your field, if your reservoir is performing how other fields and reservoirs in that area are doing. And then there's also a cum production versus cum injection plot, which is really helpful in determining if your material balance is in line with what your thoughts are. I'll also go over the Hall plot. A lot of people find value in the Hall plot and in identifying how well an injector is injecting, I guess. The injectivity, quantifying injectivity for an injector. All right, so we're gonna start with the field production plot. The green line on this is your oil rate. The dark blue line is gonna be your water production rate. The pink or magenta is your injected water rate. The little red X's right here are going to be our gas oil ratio. This black line is our producer well count, and this light blue line is going to be the injection well count. And so we're just going to kind of step through. This is for a field actually in the U.S. in the Permian region, and it's a carbonate reservoir. And I'm just going to go through and kind of step through the things that we can pull from this plot. So you can see just looking at the timeline at the bottom that it was discovered in 1946. In the first 5 years, they drilled 60 wells, and they kind of peaked out production at about 3,500 barrels of oil per day, which means that those wells were averaging somewhere between 60 and 100 barrels of oil per day. Gas wasn't reported. It wasn't required by the state at that time. But what we can see that was reported was the water, and they were producing about less than one barrel of water per day for each of the wells. So what that tells us is that there was no active water flood, or no active aquifer, sorry, and that your water saturation, there wasn't a lot of mobile water in this reservoir in the beginning. Also, you have like 60 wells that were drilled in the 1940s. So if those wells are still active, you're probably going to have wellbore integrity issues that you're going to have to deal with. The next part of the plot and the timeline, you can see we have increasing GOR. What that tells us is that the reservoir pressure has fallen below your bubble point. So you have gas coming out of solution, you have free gas in the reservoir, and you've lost your oil, or you have lessened your oil mobility. Doesn't mean that you can't water flood, it just means it's not going to be as efficient as if you had started a water flood whenever you had initially discovered the field. They did start a pilot in 1967, and you can see there are actually measurable responses to this pilot. So the first response that you see is about 6 months after the pilot started, the GOR dramatically drops. And what this means is that they've increased reservoir pressure in that area. The gas that is still free gas in the system has gone back into solution, into the oil solution in that area. And then following that, about a year later, they got an oil bump. And shortly after your oil bank or your oil bump, they got water breakthrough. So this is a proven water flood success. And it's not surprising that just a few years later, they did a flood expansion and continued to see the same kind of measurable success that they saw before. What you will notice then is that these well counts are not, they don't exceed the original 60 wells that were drilled in this field. So more than likely, all of these injection wells were converted to injection. So they were previous producers that were converted to injection. So again, at this point, these wells are, 25, 30 years old. Again, you're gonna have to consider wellbore integrity issues as the wells age. So shortly after they started the flood, or they expanding the flood, they did an infill program. They did not drill any new injectors, but they did kind of double the number of producers. So more than likely what they were doing is down spacing, which would result, if your wells are closer together, then your injectors don't have as far to go to support the producers. So you would expect to see water breakthrough faster, and you expect to see oil breakthrough faster as well. And you get that oil and water jump in response to that. Now, if these new producers follow the same primary decline as what the original producers drilled in the field did, then you would have expected to see oil start to fall off pretty rapidly over the years. Instead, it's maintained, and so all of this shaded area are kind of the reserves that you've gotten from a water flood, from having an active water flood. So after drilling all the wells, or the infill program, they kind of left everything, the field alone for about 30 years, came back and drilled some horizontal wells, which resulted in down spacing. And when you kind of introduce horizontal wells into a water flood, depending on how you place them, you're basically kind of messing up your uniform patterns. So the horizontal wells that they drilled, I can just tell you, they kind of went diagonally across across the field and ended up making several of the patterns irregular. Let's go with that. At the same time, you can see that injection rate has increased, but our well count for injectors have not increased. So this water increase is either that they found additional water in which to inject, or more than likely they did cleanouts and increase the volume in which they can inject. The importance of knowing about the cleanouts is that it means that the water that they're cycling is not being cleaned as well as it needs to be cleaned. There's probably an economic reason with that, but it's causing the injection perfs to get plugged over time. So it's something to look out for again in the future. And then the last thing that they did is they started increasing their number of injectors as well. It's kind of down spacing the patterns that were in existence. Again, they're not exceeding their well count. So these are not new drill injectors. These are most likely CTIs or conversions. All right. So what we get from that field is that we know it was under primary depletion to begin with. as the oil rate dropped off for pressure, you can say that it was most likely a pressure drive. Once it fell below bubble point, you started losing oil mobility as gas came out. And we had a very good response to water flood. And it's just a really, there are lots of things that you can take away from this just by looking at this production plot and determining what you're going to have to handle in the future operationally. So the oil rate versus cum oil plot, this is one I said that you can use roughly to kind of determine reserve numbers, and I'd say gut check them against your other methods for determining reserves, whether it's decline curve analysis or modeling or whatever. But you can see I've drawn some of the tangential lines and identify the different phases that happened in the field. So your primary recovery in this field, if they had done nothing, they hadn't done the infill drilling or the water flood or anything, it would have been around 9.4 million barrels of oil. You can see the jump in what the pilot did, and then you can see the water flood expansion as well as the infill drilling, how it's just pulling it out. What I will say is that once you start injection with a water flood, your producers are no longer so your producers become dependent upon a water flood support. So when you inject water and you start to get that producer's response, your producer's rates will track with your injected water rate. And the reason I'm bringing that up here is because when you're doing decline curve analysis and even drawing the tangent lines here, this tangent line or even a decline curve at this point would be dependent upon your injection rate. So as soon as your injection rate changed, this line or your decline curve would no longer be valid. But what you can take away from this plot as well is you can, as I said, you can do the kind of the quick and dirty EURs, and you can create or calculate your S&P ratio, which is another good way to compare with analog fields, just to see if your secondary recovery is comparing to what other fields are doing, which could point, if it's not, if you're severely below, then it could point to, hey, maybe I need to look and see what those other fields are doing and kind of replicate it because they're doing way better than what I am. So this plot goes into voidage replacement, in which you are determining your reservoir fill-up. That's what it's about. So voidage replacement has to do with when you produce from a reservoir, you're creating a voidage within that reservoir. And when you inject, you are replacing that voidage or filling it up. Ideally, in a water flood, you want to have your VRR to be equal to 1. So everything that you've produced, all the fluids that you've produced, you have replaced with injected water. And so that's why I have the 1 I kind of highlighted here. In reality, most operators will aim for a 1.2 just because they're assuming that injectors are not going to be 100% efficient. There will be some amount of injection water that doesn't make it to the reservoir, either from losing water behind pipe or behind casing or down the hole, or something that just kind of leaks off the edges of your reservoir. So usually operators will aim for a VRR of 1.2, and they'll use that target to determine what their injection rates will be. Yep. So the blue line here is your instantaneous VRR, or it's your monthly, what you calculate on a monthly basis, and the red line is your cumulative VRR. And generally what you always want your instantaneous to be at 1 or above, but the goal is to get your cumulative back up to 1 so that you have restored your reservoir pressure, or to hold it above 1 or above 1.2. Right, and then for the few that like formulas, this is how to calculate your VRR in a more detailed manner. As I said before, it's really just your injected volume divided by your produced volume, but there's more that goes into it, right? All right. Next plot we're going to look at is recovery factor versus injected pore volume. So this has to do with how well you're sweeping your reservoir. In this plot, you can see before we started injecting, you got a recovery factor in this field of probably about 5 to 7%, which is in line with what you would expect with that kind of carbonate. And over the 40, 50 years since they started injecting, they'd only injected about half of the pore volume. And that had resulted in an increased recovery factor to about 12% or so. So this tells you a couple of things, right? So if you took it that this curve trend will maintain, then you could say if my target recovery factor is 25%, then I'm going to need to inject another 3 times. Is that right to get it? Doing quick math, that's never a good idea. So if you had to inject 50% of a pore volume to get 5%, in order to get it up another 15%, you'd have to inject a total of 200, right? To get it around 25% recovery factor. So it kind of gives you a trajectory that you can follow and what you can expect to get to your target recovery factor. This is also a really good plot to compare to analogs, because again, analogs tell you if someone else is doing it better than you, or if you're in line with what everyone else is doing. So an analog comparison of this field shows that, hey, we are actually on trend. We're getting the same kind of slope that other people are getting, and what we can expect for a field is somewhere in the 25 to 30 range. But again, that's going to take the 150 to 200 percentage of your pore volume injected. So again, this is a carbonate field. If you're in a really good sandstone, you may not need to inject a full pore volume of water in order to sweep down to residual oil. It really just depends on, the mobility of your fluids and your reservoir properties. All right, and this is the last field plot that I have. So this is the cume production versus cume injection, and it's really a quick look at your material balance, and therefore it's most valuable after you have achieved fill up. So if you're following the straight line trend, then you are producing everything that you're injecting volume wise, and so you have a balanced, or a material balance is good, it's ideal. If you start to concave up, then it means that you're getting flow from outside of what you believe is your reservoir, right? So you're getting influx from something like an active aquifer. You're producing more than what you inject. And then if you're concaving down, then you have reservoir leak off. And what that means is you're producing less volume-wise than what you inject. So either your injectors are not efficient, or you're losing volume into a thief zone or into an aquifer. So what this allows us to do is just look into, hey, is something wrong with our wells if you're getting the reservoir leak off? Or, hey, do I not need to put as much energy in injection because I have natural support through an aquifer? Okay, and this is the last plot I'm going to go over. This is a Hall plot. And this is something you do just for an injector, and it's to identify your skin for the injector, or basically what your flow is between your injector's wellbore and the reservoir. So there are a couple of things to note when dealing with a Hall plot. It's assuming your mobility is 1. And then before fill up, it's going to concave up because this Y integer is assuming there are constants which are not constant before fill up. So after fill up, they become constant, but before fill up, they're not. So it creates the trend to concave up. After fill up, if your mobility is greater than 1, you're going to concave down. Mobility is less than 1, you're going to concave up. But the good thing about this plot, what it can tell you is if you're starting to see like this gradual upward trend, then you're probably getting plugging of perfs. And if you see a rapid break in the negative skin direction, then you're probably seeing fracture growth. So if you have plugging of perfs, then maybe you need to go acidize your injector, clean it out. If you have fracture growth, then maybe you need to reduce the rate at which you're injecting. Right, and that's kind of the full agenda of what we covered. We went over basic water flooding, water flood patterns, geology, reservoir fluids and properties, how they affect your efficiency, and just touched on some surveillance plots. So I'll now open it for questions.
Okay, great. Thank you, Vanessa, for this great presentation. Actually, we've got too many questions. I will try to cover them all. Okay, so yeah. The first question, okay, in case we have a small thickness of oil, will it be feasible to use a pattern injection, or will it be better to use peripheral water injection?
My preference is always pattern injection just because you have a lot more control. I've had fields where we had peripheral injection in place, and one well would inject 3 million barrels of oil over a few years and saw no response from offset producers. So I'm always going to recommend pattern injection over peripheral.
Okay. So the second question is that what is the impact of voidage replacement ratio on the reservoir pressure in terms of building up or drawdown?
So as your voidage replacement approaches 1, your reservoir pressure should be increasing, and it will make it harder to inject. So your instantaneous voidage replacement will be coming down as reservoir pressure increases, just because when you're injecting, you're limited by your surface equipment capacity. And as you approach those limitations, and you're limited in the volume that you can get down. I think that answered it.
So the next question, is there a specific type of water used for certain type of reservoirs, or it is just fresh water used always?
It's not just fresh water used always. I think it really depends on, so the practice that I've seen is it really depends on the operator and what they're doing. Salinity can have a pretty dramatic effect on wettability and how much your fluids are mobile in the reservoir, but not many people look into it, to be honest. Usually people will start with either fresh water or brine, whatever they have available. And once you start producing water, once you get water breakthrough, then they just clean that water up and re-inject it. And the thing is, like on the salinity, it really varies depending on the reservoir. There are like so many things that go into it. There's a company called ESAL that does, so that's ESAL, does really good research into this, and they could help you in determining what's the best type of salinity for your reservoir. But there's not a one answer, okay, unfortunately.
So it's usually like the lower the salinity, the higher the wettability, right?
It really depends on the reservoir.
Okay.
There are so many factors that go into it. There's really not like a one answer, unfortunately.
Okay. So another question, how high is the pressure of the injector well compared to the production well?
How high is the pressure of the injector
Yeah.
compared to the what? I'm sorry.
He is asking like how high is the pressure of the injector well compared to the production well, like the ratio between them.
Hmm.
Between pressures.
It will depend on your rate, really, and how you're producing. So with your producers, you want to draw them down as much as possible, and that has to do, so if you have like an ESP in it, then you can have a much lower drawdown pressure in a producer than say a gas lift or rod pump. In an injector, it's going to be significantly higher, just because you're forcing this large volume of water down into the reservoir. So it's really hard to say. I would assume that injectors bottom hole pressure is going to be in the thousands, and you would want to keep or thousands of psi, and you would want to keep your producer as low as possible, which is going to be depending on your surface or your production equipment that you have installed in it. But I would say sub 1,000 if possible.
Okay. Okay.
So the delta in that is like 1,000 plus in psi.
Okay. So another question, what's the impact of the pressure boundary on the producer wells located between the two injectors?
So once you introduce the injectors, then you're changing kind of the flow dynamics of the system. So there's still some kind of balance between your pressure boundaries and your no flow boundaries that dissect your injectors and your producers. It's kind of like an open-ended question. It's hard to. They will change with injectors because your injectors will kind of dominate your flow. Something more specific. I'm not really sure how exactly to answer that.
Okay, no problem. So yeah, so we have a long question.
Okay.
Have you ever encountered fields where water flooding is historically considered as EOR method and where some other wells not necessarily on the same hydrocarbon reservoir in a way became over time candidates for WSO?
WSO.
As you mentioned at the beginning of your presentation, that water preferential flow path is water-bearing layers. The fluid used for water flooding, water including additives eventually, might interfere with wells where WSO would be of interest. If you ever encountered that, what comments could you share?
You know, I'm not actually sure what WSO stands for, so I don't think I've heard that acronym before. Can whoever asked that question kind of clarify what is WSO?
Yeah, okay. So, Tere Maisonabi, could you please clarify your question? So another question, let's say we have one producer and one injector, and we inject water, and water go to two sides of its wellbore, and water go to producer side is significantly less than the other side. Is this condition, what can we do? In this condition, what can we do? As we inject water, which come from the reservoir, it is okay, but if we use other source of water, what can happen? Incompatible or uneconomical?
Yeah, whenever you're looking at other sources of water to inject, you should always test the compatibility in a lab. Usually, you're not going to have problems finding some kind of source that's acceptable. A lot of times, fresh water is used just because it's generally compatible with any reservoir. But you know, that can be costly using fresh water.
Okay.
Yeah.
So another
I think that
question
was the question.
is free gas and gas are similar?
Oh, no. So free gas, if it migrates to
Oh, Vanessa, we can't hear you.
I think the question is, do you get better efficiency in sandstone?
Yeah, so that's what they're trying to ask.
Okay. Maybe. You generally will have better flow in a sandstone than in a carbonate. So in a sandstone, I've seen a response time in as little as 2 weeks. In a carbonate, it could take, you know, 1.5 years to get a response time or longer. The more influencing factor will be how much has been produced from the reservoir, because usually you're not going to see that oil bank or that oil response until you get kind of close to achieving fill up, at least in your localized zone around your injector. So, but I would generally expect, just because the flow is better most of the time in a sandstone, to have better response and better efficiency in a sandstone.
Okay, thank you so much. I think Qasim is back. He's joining us again, and I'll so Qasim, you can carry on with the questions.
Okay.
Yeah, sorry for this technical problem.
No worries.
Yeah. So one of the questions was, what is the best water simulator in your opinion?
I don't think there is a best, to be honest. It depends on what you're trying to do when you're simulating, and so like what your goal is to achieve something and what conditions you're trying to model. So I've used, my personal preference, to be honest, is ResGrail, or Reservoir Grail, and that's because it's so quick. It's very quick. So a model that may take months to create and simulate in something like Eclipse or CMG, I can do in weeks in ResGrail, or days, depending on what it is. But I don't think there's a one model fits all category. So ResGrail is really great for like dead oil, but it doesn't handle gas well. But again, you have that time, the amazing time efficiency on ResGrail. For Eclipse, it ties into Petrel RE really, really well. So it's got benefits in that. Or you can do, if I was going to do a sector model, I would probably choose either Eclipse or CMG. CMG is really intuitive, a lot more intuitive than Eclipse or Petrel is. So I mean, they all have pros and cons, and it really kind of depends on what your goal is when you're modeling.
Okay. So for those who asked some questions, I can't view them. Could you please ask them if you still have such questions?
Hello. I'm from Myanmar, Tamiat. I want to ask about what the reservoir pressure is below the bubble point. We may have solution gas as a free gas in reservoir. One thing I am not clear is that whether it default in solution or not in the reservoir. When it go to the surface to tubing or pipe, it will lose pressure anyway. And solution get cut out of the solution. So what is the difference between the pressure losing below the bubble point in the reservoir and in the tubing around the well to the surface.
Okay. So I want to make sure I got your question right. What's the difference between losing your pressure in the reservoir versus in the wellbore? Is that right?
Yes.
Okay.
And yes, pressure in the wellbore and in tubing to the surface. Yeah.
Right. Okay. So if you had a preference, I would rather lose the pressure in the wellbore or in the tubing, just because your oil is no longer restricted by your rock, and you don't have that flow restriction anymore. When you lose the pressure in the reservoir, you have the chance of making your oil less mobile, and then it's harder to flow through the pore throats. And so that's what kind of restricts your flow the most. When it's in the wellbore, then you have other mechanical things that you can do to help the oil along and get it to surface.
Okay. Thank you very much for your answer.
No problem.
So yeah, the next question, please.
Vanessa, can I ask a question?
Yes.
Yes.
My name is Thierry. I'm the one who was asking about the acronym you didn't understand, WSO, which means water shut-off. So my question was, I was asked many years ago to design a water shut-off campaign for some wells where we had in the same, let's say, field, not exactly operated by the same people, nor the same country, but where we got injection, water flooding performed by an operator on another country, basically flooding a bit some of the wells we were operating, and where we got that were not they were not the same reservoirs in terms of oil, but still, as the water is flowing through the water-bearing zones, they were coming and rising up our oil-to-water contact, and of course, flooding into our wells where we didn't want water indeed.
Mm-hmm.
So have you ever experienced that? And if so, what kind of feedback in terms of modeling, and in particular, how to assess the interactions with, let's say, uncontrolled interactions between reservoirs?
Yeah. Unfortunately, there's not a lot that you can do to control the interaction, out in the reservoir, right? What you can control is where the reservoir is feeding into your wellbore. So the closest thing that I've experienced is in Egypt, there is a zone called the Karita, and in some locations, it's a very, very strong aquifer drive. And but it also has oil. So generally what they would do is they would drill the well down to the Karita and produce the wells for about 6 months and get all that oil production. And then when the water hit, set a plug, recomplete up zone. Now, if you ever had that plug not sit properly or not stay intact, then you get the water zone or the water influx back in your well. So I think since you can't really, or I won't say you can't, I don't know of a way that you could really affect the reservoir or how that interaction, that water zone is affecting your reservoir. I would assume that what you would really want to do is just kind of plug off or isolate the areas or the zones in your producer that are getting that water come in. And there are profile logs or spinner logs, temperature logs that you can, temperature log might be a good one, that you can run that will identify where that water is coming in from. And then that would let you know where you need to either do a cement squeeze to kind of isolate the wellbore from that area or set a plug to
now
isolate
you're talking about vertical wells, right? Because
yes,
in the
vertical
case I'm
wells.
thinking about what was horizontal drains. So we can identify the tip too and whatever,
Yeah.
but the problem is
Yeah,
indeed
with a horizontal well, that
where the
sucks.
water comes from. Yeah, exactly.
Yeah.
Where it come from, and when in this case the Iranians were decided to flood to perform water flooding or not, because that was drastically changing our wells on the other
Hmm.
side of the border. But anyway, okay, thank you for your input. Thanks.
Yeah, sorry.
Okay, the second question, what is your experience in water flooding really low permeability reservoirs, like 1 millidars?
Generally, it's not, I don't have any experience in doing uh, really low perm floods. The reason for that is that the amount of time that it takes for you to get water into the reservoir and to have it sweep to your producers is so long that the operations usually become uneconomic. The rule of thumb that I was always taught is that if your field's perm is like less than 3 millidarcies, then you shouldn't try bothering to water flood it. So most of the water floods that I've dealt with have been 3 millidarcies or higher. And the floods or the potential floods that I've evaluated that were less than that were low perms, my recommendation was not to water flood them.
Okay, so another question, how do you estimate the incremental oil production or percentage of STOIP above primary recovery you can achieve by implementing water flooding? This pertains to sandstone, solution gas drive reservoirs.
Yeah. Analog is the best way to do it, just because it's been proven. Any other kind of estimate is a best guess. But what you can look at is, let me think. Usually someone's already tried it before, but if you can't find an analog, what you can kind of do is create your own analog via a pilot flood. So if you create a pilot flood and see how the producers respond, then you can kind of extrapolate that to a bigger flood. But other than that, just doing calculation, I mean, you could model it, but without some kind of actual reality to tie it to, your model is just going to be guesswork again. So I would say you want to tie it to reality as much as possible, either through a pilot or an analog.
Okay. So I think we have like the last question. Yeah, yeah, please.
Vanessa, Thierry again.
Yes.
Related to the question about the 1 millidarcy, you put a trigger at 3 millidarcy, is that correct? In this case, why not proceeding to a quick stimulation to increase your reservoir and then reduce your flooding time? To increase your reservoir.
Like I said, the 3 millidarcy is really just a rule of thumb that I was kind of taught. You could stimulate your reservoir. Depending on how you did it, if you were basically fracking your reservoir, then you've increased your perm in the fracks. If you're trying to stimulate in some other way, like injection, or not injection, acid injection, then you're really only doing a localized improvement. And so you'll get that cavity of water around the water flood or around your injector, but it won't permeate throughout the rest of the reservoir. So you're still going to hit that block.
Yeah, my idea was more to initiate. The problem with 1 millidarcy is to initiate the flow. So if you start increasing even on the wellbore, near wellbore, then you can frac, you can propagate by yourself by increasing the pump fracture, increase the fracture, and then initiate your flow of water. For how long? Of course, it will not be indefinite time. I agree with you, but it's something that's valuable economically or not, from your experience. I mean, the fields you have dealt with.
Right. The problem with fracking or injecting to the point of fracking is that you're creating these pathways, these high pathways towards low pressure areas, right? And your low pressure areas should be your producers, unless you have like an overriding maximum stress that's going to dictate your direction. But when you do that, then you've created a superhighway directly to your producer. And while you will get some oil flush from inhibition, I believe, you're still not really flooding the reservoir. You're just flooding the fracture. So you can do that, and you will get some oil from it, but you're also going to be watering out your producer pretty quickly.
Yeah, indeed. Yeah, you're right. Okay, thank you.
Okay, so I think we have a comment from George. He's saying tight reservoirs, the line drive is okay if the reservoir has a relative good porosity and permeability, like permeability equal from 5 to 10 millidarcy. If the reservoir is tighter, less than 1 millidarcy, then the orientation of the producer should be perpendicular to SH max to take advantage of the acid frac stimulation. The injectors should be longer and parallel to SH max in low permeability reservoirs.
Cool. That wasn't a question though, right?
No, it was a comment.
Sharing info, right?
Yeah.
Okay.
So yeah,
Yes,
with this, we
fair.
came to an end for our webinar today. Thank you, Vanessa, for this great presentation. And thanks
Thank you.
everyone for your attendance and for your valuable questions.
Yes, thank you for the questions.
Please make sure to follow us on all our social media platforms on LinkedIn and Instagram at SPE by Intersection in order to get notified for all our future events. And until we meet again, stay safe and see you soon. Thank you, everyone.